You treat your smartphone like a technological peak, but really, you're pressing your ear against compressed chemistry. A tightly packed chemical block, always one failure away from self-ignition. We have pushed lithium to its final physical limit, where stability is barely more than a fragile promise. So, why does the world still cling to this time bomb? What is the real price of convenience? And what is ruthless enough to kill it? Welcome to Everyday Things Explained. The ion subway. A lithium-ion battery is not a quiet block of stored energy. It is more like a rush-hour subway station, crowded, tense, chaotic. Lithium-ion's restless little migrants keep running between two electrodes. They are pulled back and forth by an invisible force, electric fields. When you charge a battery, you are not simply adding power. You are using pressure to stuff ions onto one side, like forcing a crowd into a train car already full. The problem is, between those electrodes sits a very thin barrier, a fragile polymer film, acting like crowd control. If that separator tears even at one microscopic point, everything ends fast. Two ion flows collide. Chemical reactions erupt. Heat rises, and the battery enters a state called thermal runaway. It is a chain reaction. Heat speeds reactions up, and faster reactions create even more heat. That cycle continues until everything slips beyond control. Physically speaking, this is not exactly a normal fire. It is structured self-immolation where the battery feeds on itself. Plastic melts, metal glows red, and sometimes flames shoot out like a tiny torch, right inside your pocket. The physical ceiling. But this danger, frightening as it is not the main reason. It is not the real reason lithium-ion will be replaced. The deeper problem is colder than fear. A physical ceiling, a hard limit, one we cannot break. Lithium-ion energy density is already very close to its theoretical limit. Put simply, we have packed almost all possible energy inside. It is like cramming more luggage into a locked suitcase. You might force in a little more, but safety pays. Every increase in energy density also increases risk. More short circuits, more heat, less overall stability. Physics is rude like that. Energy never simply disappears. It has to sit somewhere. And inside lithium-ion batteries, it sits beside flammable materials. That is the inevitable result of pushing chemical systems too far. You cannot get more energy without paying in risk. The fragile supply chain. Once physics blocks the road, the battle moves elsewhere, into economics and geopolitics. Lithium is not rare, but it is not easy to extract. Cobalt, a key material for battery stability, is even more complicated. Its supply is concentrated in only a few regions, and that makes the entire supply chain dangerously fragile. Imagine the whole world relying on just a handful of mines, like one supermarket selling rice for the entire planet. If that chain breaks through politics, disasters, or rising costs, everything built above it begins to shake. Electric cars, phones, grid storage systems, all of them depend on these materials. And the price is not just money. Lithium and cobalt mining consumes water, damages ecosystems, and creates costs you never see on the bill. We call it clean energy, but the system behind it is not exactly clean. The solid-state successor. To escape that grip, engineers started chasing a new structure, not improvement replacement. And that is where solid-state batteries enter the story. A simple-sounding idea, brutally unfair to the old generation. Lithium-ion batteries use a liquid electrolyte, flammable, volatile solution, highly sensitive to heat. Solid-state batteries remove that part entirely. Instead, they use a solid material, more stable, less reactive, and most important of all, it does not burn. If lithium-ion is a chemical swamp wet and eager to ignite, then solid-state is a hard concrete road. The ions no longer have to wade through mud. They move faster, straighter, and with less risk. The result? Higher density. Longer life? Far less fire risk. But the reality is, this technology is not perfect yet. Costs remain high. Manufacturing stays difficult. And many problems are still unsolved. So while waiting for the future, we keep living with a paradox. You carry an extremely smart device every day, powered by a technology that has already hit its ceiling. Lithium-ion is not disappearing because it is terrible. It is disappearing because it finished its job as a bridge. We have squeezed nearly everything from element number 3, and there is not much left to squeeze. Technological evolution has no room for mercy. What once stood at the top will become a relic. The lead-acid paradox. Lithium-ion batteries are dying. But before you think you understand the whole story, notice one small detail. Almost ridiculous. Electric cars worth hundreds of thousands of dollars, symbols of tomorrow, still rely on a 19th century lead-acid battery. A technology supposed to be obsolete is quietly keeping the future alive.